Hi, my name is Joanna. I'm a graduate student in Dr. Dongmao Zhang's group. In this video, I would like to give you an overview of the Polarized Resonance Synchronous Spectroscopy, PRS2, which is developed in our group. First, let me give you some background. Material absorption, scattering, and emission are common optical properties that are important for material characterizations. There are many existing instruments specific for detecting different optical properties. UV spectrometer is frequently used for absorptions measurements, and IRS, DRS, and MORS are scattering intensity measurements, where the particle size and molecular weight can be deduced. And fluorescence spectrum is measured by a fluorometer. But these techniques tend to assume these optical properties are isolated phenomena, like you will only detect the absorption with UV spectrometer, and the signals picked up by the IRS, DRS, or MORS are exclusively scattering. But this concept can be problematic because in the UV region, light absorption, scattering, and emission are entangled, which means at the same wavelength, the material can absorb, scatter, and emit light simultaneously. For example, what a UV spectrometer measures is the attenuation of the incident light after passing through a sample, which gives the photo extinction. For small molecules like rhodamine dye sample, the attenuation of light can be assumed entirely due to sample absorption, because the scattering is negligibly small due to small molecular size. However, if the particle size is large, like nanomaterials, aggregates, the light attenuation is caused by absorption as well as scattering. A UV spectrum only tells you the sum of both at each wavelength, but it cannot separate how much is due to scattering and how much is due to absorption. So here's the problem. Absorption and scattering are fundamentally different. While scattering can indicate particle size, the absorption tells you about the chromophores embedded in the nanoparticles. And only absorption is related to the inner filter effect imposed on the fluorescence spectrum and the fluorescence continuum. Current scattering measurements have several limitations as well. First, most of them are intensity measurements, which means they do not measure the absolute scattering activity, which is scattering cross-sections. Take resonance light scattering (RLS) as an example. It detects scattering at the same wavelength as excitation with the fluorometer. Only a fraction of the scattered photons is detected at 90 degrees. Most photons are scattered at other directions and escape detection. Second, these intensity measurements are instrument-specific, which means what you get is highly dependent on the instrument response. For example, polystyrene nanoparticle is a Rayleigh scatterer. You can see a typical Rayleigh scattering spectrum taken with the UV spectrometer, but its RLS spectrum taken with the fluorometer has a different spectral shape, which is not an exponential decay because the signal is modified by the instrument response. Also, absorption can mess with the scattering measurement by the inner filter effect, IFE. The black chase is the scattering intensities from the pure PSMP sample. And if I add a light absorber, a chromophore called DMPH, the PSMP scattering intensities drop at where the DMPH absorbs. So you can imagine if the IFE is not corrected, the scattering will be underestimated. And fourth, under resonance measurement conditions on resonance fluorescence, ORF can be detected. ORF occurs when the fluorophore absorbs and emits at the same wavelength, which basically is the overlap region of the absorbance and emission spectrum. This Gaussian peak of rhodamine 6G detected in the RLS mode is ORF but not scattering, because it's a small molecule and you can see no detectable scattering and other wavelengths. Therefore, the RLS should be called RS2, resonance synchronous spectroscopy, because not only scattering can contribute to the spectrum. The fluorescent quantum dots give us a good example of how ORF convolutes with scattering. Imagine if you deduce the particle size under the ORF active region, you will overestimate the size of the particle. And PRS2 is a new spectroscopy method that can address all these problems. So what is PRS2? It is similar to RS2, where the excitation and detection wavelengths are kept identical while they are synchronously scanned across a broad wavelength range. The only difference is that linear or vertically polarized light is used for excitation, and the signal is detected with vertical and horizontal polarization to acquire VV and VH spectrum. The ratio between the VH and VV corrected by the G factor is the degree of sample depolarization. Different samples can depolarize light to a different degree. If there is no depolarization like the spherical gold nanoparticles, the scattered light will be picked up by VV, and no detectable intensities will show up in the VH spectrum. If the scatterer is rush-like, like the gold nanorods, the light will be partially depolarized. Then the depolarized photons will be picked up by the VH. Therefore, the scattering depolarization can provide information about the particle geometry. And if the direction of the polarized light are totally randomized by the fluorescence process, the intensity in the VH spectrum will be equal to that in VV. In addition, if we know how much light is depolarized, we can deduce the globally distributed photons and quantify the cross-sections, rather than just provide intensity measurements along one direction. In summary, we can obtain 6 new optical parameters with the PRS2. When combined with UVB spectrometry, we can decompose the total extinction into absorption and scattering components. Now you can see which part belongs to the absorption of the chromophore and which part is due to the scattering from the nanoparticles. And if the sample is ORF active, the ORF depolarization, cross-section, and quantum Eve spectrum can be quantified as well. I will not derive these equations in this video, but you're encouraged to read our publications on the PRS2 methodology, and we will have another video to explain it. So, what are the applications of the PRS2? First, characterizations of optical properties for optically complicated materials like nanoparticles, polymeric samples. Second, any processes that involved with change in light scattering, absorption, and emission can be monitored by the PRS2 technique. So far, we have demonstrated 5 applications in gold nanoparticles, porphyrin assembly, small solvent molecules, aggregation-induced emission, and fluorescent quantum dots. In the following slides, I will talk about these applications. In the application of gold nanoparticles, we quantify the scattering, absorption, and extinction cross-section spectrum for the gold nanoparticles of different sizes and shapes. For big nanoparticles, the scattering is not negligible, and it increases as the nanoparticle grows bigger. On the other hand, scattering depolarization is sensitive to the geometry. When the nanospheres transition into rods and longer rods, the scattering depolarization increases from 0 all the way to 0.4. With this finding, PRS-2 was applied to in situ monitor the gold nanoparticle aggregation process. We can see the size evolution of the aggregates through scattering cross-sections, and the light scattering depolarization provides a simple measurement of the shape evolution, which first increase and then drop. The most likely reason is that the nanoparticles first form dimers or trimers that are likely rock-shaped and finally agglomerate into a globular shape. Then we switch from studying gold nanoparticle aggregation to molecular aggregation. This work demonstrates PRS-2 is an excellent tool to follow the porphyrin assembly and disassembly processes. You can see that PRS-2 can pick up the scattering change immediately after the onset of aggregation, while nearly no change was observed in the UV spectrum, indicating PRS-2 is around 20 times more sensitive than the UV spectrometry. The scattering cross-sections visualize how the size increases during assembly and decreases during disassembly. And from the scattering depolarization, we know the time course of the porphyrin molecules assembling into tubular aggregates, and the aggregated porphyrin disassembling into shorter tubes. And then this work is the first successful determination of the light scattering depolarization and scattering cross-section spectrum for 20-line model solvents in a large wavelength region. We obtained several new insights. First, the scattering cross-sections followed Rayleigh scattering. Second, the scattering depolarization is sensitive to the molecular geometry. The rock-shaped carbon disulfide has a scattering depolarization as large as 0.5, while the globular carbon tetrachloride has zero scattering depolarization. Actually, these two molecules have identical point symmetry, which indicates that the scattering depolarization is defined by the electron density distribution but not the point symmetry. We also study another unique kind of aggregation phenomenon called aggregation-induced emission, AIE. The AIE reagents are non-emissive in their isolated form, but become strongly luminescent in the aggregation form. Addition of poor solvent is a simple way to trigger aggregation and therefore fluorescence. Higher degree of aggregation gives more brightness, but why the emission can be enhanced by aggregation? Is it because of increased absorption or increased fluorescence quantum yield? With PRS-2, we were able to answer this question by spectral decomposition. It turns out that the absorption stopped increasing at certain solvent percentage. So the increasing fluorescence intensities are due to increasing fluorescence quantum yield. And interestingly, we found that the molecules take some time to aggregate upon addition of poor solvent. During sample incubation, the UV spectrum is changing, but we don't know what is going on. With PRS-2, we understand that the aggregates are growing in size as revealed by the scattering extinction, and also the shape keeps changing as indicated by the scattering depolarization. However, its absorption is decreasing, which indicates the fluorescence quantum yield is increasing during the sample incubation. The PRS-2 allow us to understand the mechanisms and kinetics under these processes. The last example application is to study the effect of shell coating on fluorescent quantum dots. The quantum dots we study have ORF contribution to the scattering signals in the PRS2 spectrum. With PRS2 or pulse, which we will talk about later, the ORF can be separated from the scattering, and the cross-sections of all these optical properties can be quantified. We studied the effect of different shell lengths for quantum rods and the shell thickness for quantum spheres. It turns out the QD scattering does not follow Rayleigh scattering and increases quadratically as a function of the shell volume. And the scattering spectrum shares features with the absorption spectrum. Also, the shell coating can enhance the photoabsorption and ORF in the core region, but the effect is quite different from the rods and the spheres. For rods, the shell elongation does not have further impact for the absorption or the ORF once the shell thickness surpasses a critical volume. In contrast, increasing shell volume can keep increasing the absorption and ORF activities for the spheres and also cause wavelength redshifts. By dividing the ORF by the absorption at each wavelength, we for the first time obtain the ORF quantum yield. The increasing shell thickness actually reduces the ORF quantum yield for the spheres, which can be related to the ORF photon reabsorbed by the shell. Okay, that's it for this video. I will see you next time. Thank you for your time.